Hi there. I'm hoping that your first assignment went well. And we're going to go ahead and look at section 3.4, the rates. And again, you can copy these uh, from the modules, the PDF files. But let's go ahead and get started on rates. First off, a definition. We've got a rate is a ratio, a fraction, that indicates how two quantities change with respect to each other. All right, so and most of you know slope. You're changing the x and you're changing the y, and so we'll relate that here today as well in 3.5. But let's do some examples. All righty, so we have you drive 260 miles in 4 hours. What is the rate at which you are traveling in miles per hour? Now, this isn't really too hard. The units themselves tell you exactly what to do. So we're going to take the number of miles driven. Per in mathematics means divide, just like of means times. Most of you know that. So we're going to take the miles divided by the hours, how many hours we were traveling. So we take 260 miles and we will divide that by 4 hours. And again, I encourage you to use a calculator. If you don't have one, try to get one for your tests and your quizzes and your homework. Otherwise, they'll take too long because Pearson is known for not having the best numbers. Some of their numbers are way out there. All right, when we divide this, we come up with 65 miles per hour. All right, and Pearson may have you actually pick the right units as well. Some of them they do, and some of them they don't. All righty, let's move on. This next example, you're in a car with a full tank of gas and 9,312 miles on the odometer. 4 days later, you return the car with 9,630 miles on the odometer. You were charged $108 for the rental car, and you used 12 gallons of gasoline. Now, what is the car's rate of gas consumption in miles per gallon? So again, we're going to take the miles driven divided by the gallons. And again, this would be the rate of gas consumption. Well, the number of miles driven, you would have to take 630, subtract 9,312. That's going to be the numerator. That's the miles divided by the number of gallons, and you use 12 gallons. These are miles. So when you subtract those, you get 300. You drove 318 miles and you used 12 gallons of gasoline. So that when you divide those, you get 26.5 miles per gallon is what you have. All righty. So again, the units are really important when you're trying to find these rates. And again, the rate is if you change this, how much is this changed? Or if you change this, how much is this changed? So for every gallon, you went 26.5 miles. Let's look at this one here. What is the average cost of a rental per day? So here you want the cost of the rental divided by the number of days. Well, the cost of the rental was $108 total. That wasn't per day, that was total. So we'll have $108 divided by the number of days, which was 4, I believe. Yes, 4 days up here. 4 days. So we'll divide those and come up with $27 per day. All right, $27 per day. Let's go do our next rate. What is the car's average rate of travel? Now, they didn't tell us the units. It's something that we needed to do, so I added this, and it's not in your notes. You want miles per day. So you'll take the number of miles that you traveled, and the number of miles we traveled, we figured that is 318. per, so we'll divide by the number of days, which is 4. And in doing this, we get 79.5 miles per day. That's not very far, but oh well. Yeah, maybe you're just driving around in a city or something. We don't know the details, but all right. So I hope that kind of clears up how to find these rates, these average rates. Again, units, hugely important. Let's look at this next example. The route a bus takes, starts at mile marker 40 at 6 p.m. and ends at mile marker 170 at 8 p.m. What is the average speed of the car? Well, speed is miles per hour. Miles per hour. So we need to find the number of miles divided by the number of hours. So to do that, we'll take mile marker 170, subtract 40. That's how many miles. We went from the 40 mile marker to the 170 mile marker. That's how many miles. Well, let's go ahead and find that numerator, 130 miles. Now, per hour, how many hours? Well, you went from 8 p.m. Notice that corresponds to the 170. These correspond. We'll talk about that when we talk about slope. And we're going to subtract to find the difference, how long it took, 6 p.m. And that ends up being 2 hours. So when you divide those, you're going to get your 65 miles per hour. Again, we looked at the units. I did a little bit of subtraction, but it's not too hard. All righty, let's go on to our next page, see what we've got. I might use this here. I drew this in already just to kind of save some time. Here, I want to get rid of that. There, good. All right, so let's go ahead. We're going to visualizing rates with graphs. Okay, graphs allow us to visualize a rate of change. The quantity in the numerator of the rate appears on the y-axis, while the quantity in the denominator below goes on the x-axis. So the units on your rate tell you what's in the y-axis and what's in the x-axis, such as if it's miles per hour, this would be the miles and this will be the hours. You know, 99% of the time when you're doing rates with time, it's always the x-axis, always the x-axis. All righty. So where were we? Okay, graphs allow us to visualize a rate of change. Okay, we kind of looked at this right here. The y-axis is the numerator and the x-axis is the denominator below. Let's look at an example. Between 2009 and 2014, the area of rainforest cover loss in Brazil decreased at an average rate of 525 square kilometers per year. So every year, that's what it's going down because it's decreasing every year this much every year. In 2009, the rainforest loss was approximately 7,500 square kilometers. So they tell us, you know, in 2009, what was the loss? Draw a graph to represent this information. So here is kind of, this one actually is a little tricky, but before we need to make sure that we know what each of these is going to represent. Now we know that the y-axis is how much loss we have per square kilometer. So when we do this, we'll go rainforest loss in square kilometers. Okay, that's what that represents. Now, what will we use as far as this right here? Well, we know that we're going to have to plot this right here, 7,500. So what I'm going to do is I'm going to go, and this is a judgment call. So chances are Pearson's not going to have you do this part. All right, so we've got 1,000, 2,000, 3,000, 4, 5,000, 6, 7,000, 8, 9,000. All right, that gives you an idea. Okay, now then along here, well, this right here, we know that our rate is this many square kilometers per year. What we're going to do is now this, again, this is a judgment call. Sometimes they'll start with a 1 and they'll tell you that 1 represents 2009. Well, what we're going to do is we're just going to go 2009, 2010, 2011, 2012. I'm not really sure how far we have to go. I think I'll quit there. If we have to go further, we have to go further. All right, so let's go ahead and we want to draw the graph to represent this information. To me, the hard part's over. That's coming up with this graph. So we know that in 2009, we lost 7,500. So 2009, 7,500 is roughly right there between the 8,000 and the 7,000. So now how much is lost for 2010? Well, every year you lose 525 every year. So to find 2010, we're going to have to subtract. See, I'm gonna go ahead and label this 2009, 7,500. We're going to subtract 525 from this because it decreased every year. So our slope is actually, or this rate of change is telling us if we change it a year, this is how much it's going to decrease for each year. So if we go to 2010, which is 1 year from here, this is going to decrease by this much. So we'll subtract the 525. So in 2010, we're going to have about 6,975. So right about here. Obviously, this graph is not going to be super accurate. So in 2010, we dropped by this much. Every year you move over, you drop because it's a decrease by this much. And that gives us our 6,975. Okay, and there's our next point. Now let's go ahead and do another one before we draw our line. Let's do 3 points just to make sure, even though you only need 2 to determine a line, let's go ahead and do 3. So the next year we drop again by this much. So here in 2011, we're going to have 6,000, roughly 6,000, well, okay, my graph isn't the best, I'm sorry. 2011, 6,450. Yeah, I kind of wanted it to be linear. We know it's linear because the change is a constant. So our path from point to point is a constant. And when that happens, when you're going from one point to the next point, you know it's linear. And I got a ruler here. No, so then you could draw your line that represents the loss in rainforest. Okay, perfect. That's it. We've drawn the graph. So let's go ahead and look at our next one on this sheet. Oh, I'm going to try to make sure that last video that I made, it was kind of blurry. So I'm really trying to make sure that we stay focused on this. That looks really good. Okay, Nadia prepared the graph shown below from data collected on a recent day at a branch bank. What rate can be determined from the graph? So when we're looking at the rate, we're looking at the change in the y over the change in the x. And again, soon we'll be calling that the slope. But for right now, we're going to call it the rate. So when you want to find the units or what you're finding, you look at the y-axis for the numerator, the number of transactions. So we've got the number of transactions per, I guess I'll write the word per instead of the slash, per. Now, what is the change in the x? So every time you change the x, you're changing the y a certain amount. And here, it's not day, you don't put time, you put, when you go from here to here, it's hours. When you like subtract to go from like 9 to 10, it's 1 hour. And 10 to 11, it's 1 hour. So it's the number of transactions per hour. That's what the rate. That's the rate that you can determine from the graph, is the number of transactions per hour. And what is this rate? Well, they give you 2 points, so we're going to use these 2 points. So again, is a rate is if you, okay, if you go this direction, how many hours? Well, this is from 9 to 11 is 2 hours. And then you go up. So we've got 75 to 200. So we've got 150. So I'm going to write this down. Oh, is that 200? No, it's 225. Yeah. So we went looking at the numerator, 225. Okay. And we're going to subtract 75. Okay, that was our change in our y. Okay. And then we went from 11 o'clock to 9 o'clock. That's how far the x's change. And that gives us 150 over 2. So we're making 75 transactions per hour. Change in y over the change in x's from point to point. And it's a constant. So if you were to take another point and go 2 hours, you'll also go up 150. So, you know, this rate is a constant when it is linear. And so, you know, you can also think of it as a path from point to point. Great. Now, that brings us to another idea that goes very well with 3.4. So I'll do them together, 3.4 and 3.5. And that's looking at the slope. All right, so the concept of rate, looking at the top here, the concept of rate and the slope of a line are very connected. This is what we will explore in this section. When looking at the graph of a line, the ratio of the vertical change, the y, to the horizontal change is the rate at which y is changing with respect to x. This ratio is a measure of the line's slope. And many of you have seen this, and it might be a review for most all of you. But just in case it's been a while, we'll try to go through it slowly. Otherwise, you can fast forward. All right, the slope of a line containing 2 points on a graph is given by, well, again, we use m for slope. That's just the symbol we have. That's pretty standard for slope. The change in y, sometimes we call it the rise, over the change in x, we call it the run. Now here we've got the difference in the y's over the difference in the x's. Now it doesn't really matter which point you start with, but if you start with this point in the numerator, you start with this point in the denominator. If you start with this point in the numerator, you start with the x2 in the denominator. Stay consistent. Just stay consistent. So the order of the points actually does not matter as long as you are consistent. So we're going to do a couple of examples. All righty. So example number 1. Find the slope of the line containing the points -4, 3, and 2, -6. So following our little template formula here, well, let's go ahead. Let's just start with 3. Now, this is the mistake people make that I've seen on tests, is that they do the x's in the numerator, but don't do that. You start with the y's. So you've got 3, subtract a -6. It's always subtraction. And then we have, since we started with the 3, we'll start with the -4 underneath in the denominator. -4, subtract 2. Okay, some of you have like what's called an N/D key on your calculator, and you can just plug that in. Here, 2 negatives is a positive. So you come up with 9 over, sorry, I didn't need to change that one. I was going to change the next one. -4 minus 2, -6. If you type that into Pearson, it's going to count it wrong. It does want you to reduce your fractions. And for the most part, it'll tell you underneath, write your answer as a simplified fraction. So, if it says that, don't put in a decimal because it'll count it wrong. All right, so what we have, we'll divide them both by 3. And you may have a calculator that reduces for you. It doesn't matter where you put the negative. You can put the negative with the 3. You could put the negative in between by the line, or you can put the negative there. As long as you've got a negative somewhere, it's fine. I'll put the negative with the 3. So your slope is a -3/2. So when you change the x2, you're going to drop the y by 3. You're dropping because it's a negative. So you would go to the right 2 and down 3 as you went from point to point. So because this is negative, it's a negative slope, which we'll talk about at the end of this page. Perfect. Let's do another one, just in case. Again, fast forward if you've had this and you've got it. All right, let's find the slope containing these 2 points. So I'm going to start with the 8 this time. So I'm going to go 8 minus 2. -4, subtract 10. Okay, when we do this, we'll come up with 6 over a -14, which has to be reduced because 2 goes into both of them. There's your slope. So that means if you change the x7, and I usually go to the right on that bottom one always, you're going to drop 3. Every time you change the x 7 places, the y drops by 3 from each point to each point. Okay. Well, I hope the formula makes sense. Again, make sure you use the y's, which are the second numbers in the ordered pair in the numerator on the top. Okay. Now this one right here, I'm sorry, but it's small. But if we want to find the slope given a graph, I'm going to find 2 points. You don't have to. You can actually count blocks if you wanted to. And so here you've got 4 blocks going from here to here. And then up here, you've got 3 blocks. Okay. Now that tells you what the slope is. You've got the rise, which is 3, over the run and going from point to point. And I just chose those points because those are the only ones I could tell what they were, where they cross a grid, over the x. So when you change the x4, you drop 3. Now notice the direction, and we read these lines from left to right. As we read from left to right, it's negative. All right, it's dropping, so it's negative. If it's rising, it's positive. And we'll talk about that here at the bottom, I believe, of this page. Now, what happens if you just want to find points rather than counting blocks? This right here, this point is the point 0, 3, that point. This point here is the point 4, 0. Now you can take the difference in the y's over the difference in the x's. 3 minus 0, those are the y's. The x's, 0. Since I started with the 3, I'll start with the 0 underneath. 0 minus 4. 3 over a negative 4. So, you can look at it either way. It depends on the graph that they've given you. I want to caution you, though, make sure that if you do count these blocks, that you're very careful that each tick mark is 1, because sometimes they don't. Sometimes each tick mark is 20. So you'd have 20, 40, 60 as a numerator. So just be aware of that. Watch the tick marks. Each tick mark is not always a 1. Okay, be aware of that. Now let's look at, all right, so now we're going to talk about what's a negative slope, what does it look like, positive slopes, what do they look like? Well, a positive slope means that the y value is increasing as x increases. So as you move to the right on the x, you move up on the y. So, sorry about that. So as the x increases, the y increases. As an example, if you have a point here, if the x increases, it goes here, the y increases, you go up. So as the x increases, the y increases. And so you get a slope going up to the right as you read from left to right. You read the graphs from left to right. Now, a negative slope right here means that the y is decreasing as x increases. So if you're given a point, if the x increases, which means it goes to the right, the y decreases for your point. And notice how it goes down. That's a negative slope. So this is a positive m, and this right here is a negative m. As x increases, y increases. As x increases, the y decreases. Perfect. Let's see what we've got on the next page, our last page here. Oh, okay. Now we have a couple of special cases. The slope of a horizontal and a vertical line, which we talked about in the last section, how to come up with the equation and things like that, and how to graph them. So these types of lines have very specific slopes in all cases. All horizontal lines, no matter where they're at, have the same slope. And all vertical lines, no matter where they're at, they also have the same slope. And what would that slope be and why? Well, let's look at this first example. Graph the equation y equals 4. So this is a good review of our last section. We're going to go on the y-axis, which is right there. We're going to go to 4. I'm going to put something underneath this because it's a little bumpy. About that. Just give me a second. Make sure it's focused. Yes. Yeah, it is. So we're going to go to 4. 1, 2, 3, 4. Okay, so here's our 4. And I'm going to draw, that's y equals 4. Any point that you picked on this line, whether it's 1, 4, 2, 4, 3, 4, the y is always 4. So it's a horizontal line. It's a crooked horizontal line, but it's a horizontal line. Then using any 2 points on the line, find the slope. So we're going to pick, let's say 1, 4. And let's do 3, 4. Okay, we'll pretend that's 1, 2, 3. Good. So let's go ahead and find the slope. So we take the difference in the y's over the difference in the x's. So here, the y's are both 4. And the x's, I guess we don't know which one. We will start with this one because then we have. That gives us 0 over 2. All right, now 0 over 2 is 0. And we're going to talk about that. You seem like a little kind of kind of an easy concept, but you know, it may not be clear to everyone why. Y is 0 over 2, 0. And we'll talk about this after we talk about this. So that tells us that horizontal lines, because I know that all horizontal lines have the same slope, all of these have a slope of 0. Every horizontal line, the slope is 0. And think about it, that makes sense, because the slope is the measure of a steepness. And if you're flat there, and if you're driving on a flat road, there is no steepness, it's 0. All right, so it's none, no steepness. So we call that 0, it's flat. Okay, we'll come back to this idea here in a second. All right, let's look at the next one. It's kind of getting dark in here. I might turn the light on and see, yeah, that's not bad. Okay, now we're going to graph the equation x equals 2. As a review from our last section, we're going to go to 2 on the x-axis. And here's our x-axis. We go to 2 and we're going to draw a line right through that 2 on the x-axis. We have what's called a vertical line. So we're going to choose 2 points on that vertical line. This is the point 2, 0. And let's pick one up here. We'll say that's the point. Oh, yeah. That's not 2, 0. Sorry. That's 2, 1. And this is the point 2, 2, 4, we'll say. Sure. 1, 2, 3, 4. All right. So again, I just, picked any 2 points on that line, and my 1 is not real clear. Sorry about that. That's a 2, 1. That's the point 2, 1, 2, 4. So if we use our formula, difference in the y's over the difference in the x's, we have our slope is 4 minus 1. Those are the y's over 2 minus 2. Those are the x's. We get 3 over 0. Now, what's 3 over 0? It's not 0. This doesn't seem like it's registering very well when I turn that light on, but maybe it'll work. All right, so here, this is totally different than this right here. What is this equal to? 3 over 0 and 0 over 2. Well, we're going to go up to here, and we're going to go back to your elementary when you were dividing, when you were doing long division. When you do long division, like let's say we have 6 over 3. You go 3 outside, 6 is on the inside. And 2 times 3 gives you 6. No problem. So 6 over 3 is 2, because 6 divided by 3 is 2. Okay, 2 times 3 is 6. Now here, we're going to go 2. All right. What times 2 gives you 0? Well, 0 times 2 gives you 0. Anything times 0 is always 0. So we know that just like 6 divided by 3 is 2, we know that 0 divided by 2 is 0, because 0 times 2 gives you 0. You always put this on the inside of the box. So, it works. You get 0. But what about this guy? All right, I know that the top number goes in the box, just like the 6 went in the box and the 0 went inside. So we're going to go 0, 3. Okay. What times 0 gives you 3? See, we have a problem. Okay, there isn't anything. So because there isn't anything, there's no number. 0 is a number. 0 is a number. So you can get an answer of 0, but there are no numbers where you can take what number times 0 gives you 3. It's not possible. So we call this undefined. Some people say no slope, but I believe Pearson uses the word undefined. So this is undefined. So there's a huge difference where that 0 is. The 0 in the numerator, that's possible. You get 0. It's flat. But when you have a 0 in the denominator, and to tell you the truth, this is where we have differential calculus. Differential calculus addresses this exact problem. How do we deal with a 0 in the denominator? But for right now, we're going to say that the slope of this vertical line is undefined. And, you can just memorize that if you want to. It's 0 and undefined. Think of it as, okay, this is a nice road to travel on. It's 0, but this, no, you don't want to travel on a road like that. It's undefined. So the slope of a horizontal line of the form y equals a, where a is any number, a can be, y equals a -1, -2, any horizontal line. This is a horizontal line, has this type of equation where a is a number, is always 0. The slope of a vertical line, all vertical lines have the basic form x equals some number. In this case, we said x is 2, but it could have been anywhere, is always undefined. All right, perfect. So we kind of got that straight. Let's look at our last thing for this. And these are some examples, some application problems here. There are many, many applications for slope in real life. So we're going to look at 2 of them. The head wall on Mount Washington in New Hampshire. I don't know if any of you have ever been there, climbed it, maybe you have. It drops 720 feet over a horizontal distance of 900 feet. So we want to find the grade of the slope. Grade is just the slope expressed as a percent. So sometimes you'll see roads that say it's a 7% grade. I'm thinking those of you that are in Sheridan that going up 14 is it like a 7% grade, something like that. And they have legal limits for roads as far as how steep they can be. Aberdeen Hill, I don't know. I'll have to find out what the grade of Aberdeen Hill is. But anyways, let's get back to this problem. So we're going to drop 720. The drop 720 is the y distance, and it's dropping. So we're going to go a minus 720. That's our y. That's our change in our y for our slope. I'll just put all those there. And yeah, I'm not real thrilled with that, how well it's registering those. Hopefully you can still see that. Now, and then the horizontal distance is 900. Now, Pearson, the negative, they may want you to put the negative in, or they may have they may say drop. I don't know. You just have to look, try it. Okay, now again, we're going to reduce this, and we're going to get a negative 0.8. Okay, but they want this registered as a percent, not as a negative 0.8. So they want the grade. A lot of times you'd have to change this to a fraction to please Pearson, but Pearson would want a percentage. And to change it to a percent, you move it over twice. So it's like an 80% drop. That's huge. That's huge. It's a cliff. You have to be a rock climber to handle this one. So it's an 80% grade. Okay, perfect. But again, it's just difference in the y's over the difference in the x's. Let's look at one more construction one, and then we'll be done. I was thinking about using a pen rather than the pencil, but I don't have one handy, so we'll just go with this one. A certain roof is required to have a grade of 30%. If the length of half the roof is 8, how tall does the roof need to be? To me, it's kind of hard to think, what do they mean by the 8? Well, we're going to say that the 8 is this. It's half. It's that distance right there. And the grade is 30%. And they want to know the height, which we're going to call y. We're going to stay kind of consistent with our x and y axis. So we have the grade is 30%. Well, the grade is a slope, just written differently. It's rather than a fraction or a decimal, it's written as a percentage. So I know that the change in this right here, the change in the y, that distance over this distance is the slope, and they have 30%. So the slope, change in the y's, I wonder if that went down. I don't know. Yeah, it's done. So the change in the y over the change, or the change in the vertical over the change in the horizontal, is 30%. Well, you have to get rid of percent signs before you can multiply or divide or do any of your math stuff with it. So we're going to go y over 8 equals 0.30. Sometimes I forget that 0 in front, but the placeholder. Now you're going to solve it for y by multiplying both sides by 8, and you're good to go. So we're going to multiply by 8 times 8. So y is equal to 2.4 feet. I'm trying to see, is this feet? Yeah, feet. Okay. So that's the height, which 16 feet, I guess, isn't that wide. So 2.4 feet just doesn't seem very high, but that's all right. It seems to work. Okay, well, that's it for these 2 sections. I hope that helped, and I really encourage you guys to contact me if you're having any issues, with any of the homework or any of these things that I've gone over. Just, please let me know. And my, like I say, my cell phone's on that syllabus there, or my email. Well, have a great day.